Right, we're looking at differentiating implicit functions, that stuff with y's and x's in, they're going to be differentiated, and parametric. So let's have a look at implicit first of all. Well, it kind of works exactly the same way as normal differentiation, if I'm totally honest. It's just every time you differentiate a y part, okay, dy dx kind of pops out. So if I do this first bit, y squared would differentiate to 2y, and I've differentiated a y, so dy dx pops out. Right, there is obviously a reason for this. Being a short video like this, then I can't really go into it. But here we go. When I differentiate 3y, I get 3, and dy dx pops out. Okay, and on the other side, x cubed goes to 3x squared. Now then, once you got to this stage, we want to find dy dx. So all I'm going to do is factorise out dy dx. Here we go, and we get 2y minus 3 equals 3x squared, and I want dy dx equals everything else, so all I'm going to do is this. Alright, so that really is that easy. All I would say is that often you get like x's and y's in the same bit, and you'll have to use the product rule, but beyond that it's no more difficult. As far as parametrics go, the way to do this is to find dy dt or dy d theta, it's in t's in this case, and dx dt, and put one over the other. So I'm going to find dy dt. Okay, and that is going to be 6 cosine of t. I'm going to find dx dt. Okay, and we're going to get minus 4 sine 2t. I'm presuming you don't need me to use the chain rule for that. And then dy dx is just dy dt over dx dt. So that's 6 cos t over minus 4 sine 2t. I don't need to simplify, it doesn't ask me to. I've then got to find the gradient of the curve where t equals pi over 3. So let's put pi over 3 into this. When t equals pi over 3, I get 6 cos pi over 3 over minus 4 sine of, what's that, 2 pi over 3. And stick that in your calculator, you get minus root 3 over 2. Pretty straightforward yet again. So just find dy dt, find dx dt, stick one over the other. Simples.